In this video we're going to look at how sequences can be used to model and interpret some real-life situations. So in our first example we have Lily, a Year 12 student who likes to produce a sequence to show the length of time in minutes that she intends to spend at home on her schoolwork each day starting next Monday and including weekends for the next 10 weeks at school. The sequence starts 90, 120, 150, 90, 60, 150, 0, 90, 120, 150, 90, 60, 150, 0, 90, 120, 150 and so on. So the first thing we've got to do is briefly describe the sequence giving Lily's intentions. Looking at the figures that Lily has given us, we can see that they are running through a 7-day cycle. In other words, she set up a weekly cycle. So we can describe the sequence by saying that the sequence has got period 7 because it just consists of the values 90, 120, 150, 90, 60, 150, 0, repeating each week. How long does Lily intend to spend on her work on the 39th day of this routine? Well, the 39th day of the routine is the 4th day of the 6th week. The 4th number in the sequence is 90, so the 39th day of the sequence is going to be 90. How long does Lily intend to spend on her work throughout the 10-week scheme? Well, in 1 week she plans to spend 90 plus 120 plus 150 plus 90 plus 60 plus 150 plus 0. In other words, 660 minutes on her work. So in 10 weeks she plans to do 6,600 minutes, or if you like, 110 hours of work. Moving on to our second example, we're going to consider a 3-week fitness program revolving around time spent on a weights machine and then also time spent on a rowing machine. Pause the video at this stage and just read through the details of the fitness program. And when you've read through, start the video again. Let's start by introducing a little bit of notation. Let the sequence W1, W2, W3, etc. represent the time spent on the weights machine on the nth day. So Wn is the time on the weights machine on the nth day, and we'll let Rn be the time spent on the rowing machine on the nth day. Now, we know that W1 is 15, and we know that the time spent on the weights each day is increasing by 90 seconds or 1.5 minutes each day. So the sequence Wn is going to be an arithmetic sequence with first term 15 minutes and common difference 1.5 minutes, which means that I can write down that Wn is going to be the first term plus n minus 1 times the common difference. In other words, Wn is 15 plus n minus 1 times 1.5, which simplifies to 13.5 plus 1.5n. For the rowing times, we know the rowing time for the first day is 20 minutes, and that each day the rowing time should be increased by 5% of its previous value. So that means that the sequence R1, R2, R3, Rn, etc. is a geometric sequence with first term 20 minutes and a common ratio of 1.05, because the amount of time we're going to spend on the rowing machine on a day is 1.05 times the amount of time that we spent on the rowing machine the previous day. The nth term of a geometric sequence is a times r to the n minus 1, where a is the first term and r is the common ratio. So we've got Rn must be 20 times by 1.05 to the n minus 1. So the total time spent on the nth day is going to be Wn, the time spent on the weights, plus the time spent on the rowing machine, which is Rn, plus the 5 minutes for the cooling time. So we've got Tn is given by Wn plus Rn plus 5, which is 13.5 plus 1.5n plus 20 times 1.05 to the n minus 1 plus 5, which simplifies to 18.5 plus 1.5n plus 20 times 1.05 to the n minus 1. And we can immediately now calculate that the time spent in the gym on the 10th day is going to be 64.5 minutes. For the second part, we want to get the total time over the 3-week period. So that's going to be the sum between k equals 1 and 21 of tk. So that's sum between k equals 1 and 21 of the wk plus the rk plus the 5. And we can know that we can split the summation of a sum into the sum of the summations. So we can say that's the sum of the times spent on the weights plus the sum of the times spent on the rowing machine plus the sum of the cooling down times. Now the sum of the times spent on the weights is the sum of an arithmetic progression whose first term is 15, whose common difference is 1.5, and we've got 21 terms to add. So that is going to give me a sum of a half times by 21, that's the value of n, times by 2 lots of the first term plus n minus 1 lots of the common difference. In other words, times by 2 times 15 plus 20 times 1.5. The sum of the times spent on the rowing machine is the sum of a geometric progression with first term 20 minutes and a common ratio of 1.05. And we've got 21 terms to add up. So the sum of the time spent on the rowing machine, 20, times by 1.05 to the power 21, take away 1, all divided by 1.05 minus 1. The cooling down period before taking the shower is 5 minutes each day, so that will simply give me 5 times 21 as being the total time spent on the cooling downs. And if we evaluate that, we've got 630 for the total time spent on the weights, 714 for the total time spent on the rowing machine, and 105 minutes spent on cooling down periods, giving me a total time of 1,449 minutes during the 3-week period. Our final example is a model for the number of trees in a forest, and the model assumes that the forest currently contains 20,000 trees, that each year 9% of the trees will die and be cut down, but that each year 5,000 new trees will be planted. And what we're asked to do is to produce a mathematical model for the number of trees in the forest in n years' time. And we're going to let Tn denote this number. So we've got T0, which is the number of trees now, is 20,000. Tn plus 1 is going to be the number of trees in n plus 1 years' time, which is going to be the number of trees in n years' time minus the number of trees cut down during the year, plus the number of trees planted during the year. So we've got Tn plus 1 is equal to Tn, the number of trees in n years' time, minus 0.09 Tn, that's the number of trees that are cut down during that year, plus the 5,000. In other words, we're setting up a mathematical model that says Tn plus 1 is 0.91 Tn plus 5,000. So our model, the mathematical model we have produced, is based on the iterative formula T0 is 20,000 and Tn plus 1 is 0.91 times Tn plus 5,000. So we can now calculate some of the early terms in the sequence very easily. We've got T0 is 20,000, T1 is going to be 0.91 times T0 plus 5,000, which ends up giving me 23,200. And T2 is going to be 0.91 times T1 plus 5,000, which ends up giving me 26,112. And T3 is going to be 0.91 T2 plus 5,000, which ends up giving me 28,761.92. And straight away we can see that this model is actually giving us decimal parts of trees. We can't have 0.92 of a tree, okay, but the mathematical model is allowing us that. We'd probably interpret that as being a forest of size 28,761 or 28,762. A calculator or spreadsheet will quickly enable us to calculate many more terms in the sequence. I've done it on a spreadsheet in this case. From the spreadsheet and the associated graph, we can see that the mathematical model is predicting that the size of the forest is going to be increasing, but increasing to a limit of somewhere around about 55,500 odd trees. The modelling assumptions that we've made is that the model is allowing us to have fractional numbers of trees. Much more important, though, as a modelling assumption is that we are assuming fairly constant climatic conditions. If this isn't the case, then the death rate certainly won't be a constant 9%. So some years we might have the number of trees being cut down needing to be more than 9%, and other years it may need to be less than 9%. But our mathematical model is assuming a constant 9% of the trees are cut down each year. And that concludes our look at modelling with sequences.